Okay, in this lesson we're going to talk about inverses and determinants. Alright, so first of all, let's define a square matrix. A square matrix is a matrix that has the same number of rows as columns. For example, if I had a matrix that was a 2 by 2, a 3 by 3, a 4 by 4, a 5 by 5, a 10 by 10. On page 234, they give us examples of the 2 by 2, 3 by 3, and 4 by 4 matrices, and they're all square matrices. Also, on page 234, it talks about the identity matrix. We talked the other day about the additive identity. Today, since we're multiplying, we're going to talk about the multiplicative identity. Let's go to real numbers. Think about real numbers. What is the only number that I multiply any real number by that it keeps its identity?
0, 1.
1. If I multiply anything by 1, it stays the same. Multiply it by 0, I get 0, right? Add it to 0, it keeps its identity. But I multiply it by 1, it keeps its identity. Alright, there is also an identity matrix. Identity matrix is always a square matrix that has ones along the diagonal, beginning in the upper left-hand corner and going to the lower right-hand corner, and zeros is every other element. So, note these in your packet. You'll use the one you need because, as you know, you can't multiply all matrices. So if they tell you to multiply a matrix by the identity matrix, you're going to use the appropriate one. Which one do I need? Do I need a 2 by 2, a 3 by 3, a 4 by 4? Hopefully not a 5 by 5 or 10 by 10, but if I needed it, this is what they would look like. They have ones in the diagonal from the upper left to the lower right and zeros everywhere else. Now, although most multiplication of matrices is not commutative, that's not true with the identity matrix. If I multiply a matrix, I stands for the identity. If I multiply a matrix times the identity in this order, or the identity and then the matrix, I still keep the matrix. So multiplying with an identity is commutative. That's unusual, isn't it? So I've got ones in the diagonal, zeros everywhere else. And we're going to talk about that more as we get into solving matrix equations. Today I would be glad if we could get to the point where we could at least solve a 2 by 2 determinant, and if we have time, talk about a 3 by 3. A determinant is not a matrix. A determinant is a number associated with a square matrix. So a 3 by 4, a 2 by 3, a 3 by 2, those are not square matrices, right? And so they do not have determinants. So if you're told to find the determinant of a matrix that doesn't have the same number of rows as it does columns, you're going to say, what? It's not possible, right? So square matrices have determinants. And when they do, here's the formula that you follow. This is important to remember. If these are the elements of my little 2 by 2, I start in the upper left, cross multiply, you can remember it that way. A times D, and then here's that built-in minus that we were talking about a few minutes ago, minus B times C. That's about as simple a formula as anybody can get, okay? So if this is my matrix, and I'm going to find the determinant of, how has this changed? I'm no longer doing brackets, now I'm doing vertical bars, and that is the symbol to show you that you're going to find a determinant and not refer to this as a matrix. You're finding the determinant, the number associated with this matrix. All right, if this is my determinant, I would start in the upper left, cross multiply, built-in negative in my formula right here. So that would be negative 40 plus 77. 37 would be my determinant. I don't think that's too tough, is it? A 2 by 2 matrix is super easy. Now go to a 3 by 3, 4 by 4. Ooh, it gets bigger, okay? Bigger and uglier. But a 2 by 2 is very, very simple. All right, let you guys try this one. Do the same formula. You guys agree? So today we've learned how to multiply. We've learned some more vocabulary, and we know how to do a 2x2 determinant. Okay, so that's everything we've done today. I'm going to save 3x3s for tomorrow because we're going to need some time to work on that. So let me assign